I will begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for your creation. We can understand a little bit more about it. Help us to understand a little bit more today, Lord. In your name I pray, Lord Jesus. Amen. So, this is lecture 24. I'm not sure this is even relevant today. I think I may have just... Yeah, we talked about... Yeah, that one we did last time. All right. Lecture 25 is where I wanted to be. So in lecture 25, we introduced this stress energy tensor, as you may recall. And we talked about how we can calculate the force per unit volume with it, right? And then I basically said, okay, if we integrate that force over the boundary, we integrate the stress energy tensor over the boundary as well as the whatchamacallit here, the pointing vector, right, over the volume, then that gives us the net force due to the electromagnetic force on the volume. And then I started working this example last class, and about 20 minutes later I was like, enough, you know. But I can't leave well enough alone, so I finished the example. And so let's spend 2 minutes looking at it. So here was the setup. We figured out that the surface of the upper hemisphere, there's two pieces, the top and the disc, right? The bowl and the disc, as Griffith calls it. You got to calculate. It's also fairly clear that the component, the force, is going to be in the z direction. So what that means is we're up against calculating essentially these three separate surface integrals, because really each one of these is a separate surface integral. Think about it. You know, it's a different vector field essentially. And but we got 6 of those to do, right? Because we've got the bowl, but also the disc. So we were into this. We worked it out, and so you calculate the parts of the bowl. You get what I've got here and here, and let's see here. Where did it? You know, this is all coming from. First of all, the dA dot with x, x1 hat, x2, x3 hat picks you out those cosines and sines as appropriate, and the radius squared, right? And then when we take the dot product of that with the x1 or x2 or x3 hat, it just picks off one of the components, right? So we end up with these lovely trigonometric integrals, all right? And we did derive some of this last class, right? But I didn't put it together. So if you put it together over here, add them together, it's actually stupidly simple. So I did the hard part and didn't do the easy part, which is just adding them. Once you add these, you get like, see, cosine and sine? And so that just collapses down to, sine cubed theta cosine theta, right? Like that. The reason there's a 2 here is I've factored the half out, so that made that into a 2. And then over here is your cosine squared minus sine squared, cos theta, sine theta. But then if you multiply this out, you've got 2 of these here, but you've got minus 1 of them over here, which gives you just 1 of them. And then, of course, you've got the cosine times cosine, which is cosine cubed. But then you factor sine cosine out of this, and then you just have the integral of sine cosine. So all of that, just to have integral of sine cosine. And lo and behold, there's, half of it, because we still have to do the disk. All right, so that's equation 8.23 in Griffiths. Then to do the disk, I have, dA pointing downward, which notice that S is equal to R on the is equal to 0 plane, so we have a conflation of the spherical and the cylindrical radius in this context, so I'm just going to stick with the R rather than converting everything over to S and getting confused, which was I was starting to do last time. But anyway, here it is. So this is the electric field. It's linear from the origin out on the bottom of the disk, right? Because it's the uniformly charged sphere, so the electric field linearly increases from 0 at the center out to its maximum value, and then it decays like Coulomb, the Coulomb field after that. But anyway, there is no z component on the disk, right? It's just, if you were to plot it, the electric field lines are like that, right? They're just like that. So very exciting picture, yes. All right. So then, this is a little bit easier than the other one, because if you look at it, because dA is only in the z direction this time, these two terms are 0, which means of the three things we have to integrate, only one of them is non-trivial, which means we actually only have to calculate T33, which it turns out cosine squared plus sine squared is 1, so T3 doesn't have any angular dependence. It's just radial, and you integrate that thing, and that gives you almost the same thing, but with 1/16 rather than 1/8, and then 1/8 plus 1/16 is 3/16, and there you go. So that's what we missed out on last time for that example. Now, moving on. Maybe we're moving on. No, I want to go to 26. All right, there we go. So last time, I was trying to talk to you guys about conservation laws of electromagnetics, of course. And we talked about how, the rate of change of mechanical momentum is given by the, this formula boxed in red there, right? And we introduced the momentum and the electromagnetic fields over some volume according to that formula. We're integrating epsilon naught mu naught times the integral, the volume integral of the Poynting vector, right? So that gives us the momentum in the electromagnetic fields. And then the momentum density, though, of course, is the we call G. It's mu naught epsilon naught times the Poynting vector. And we pointed out that, in empty space, the mechanical momentum is not changing. Therefore, we must have this balancing act between the divergence of the stress energy tensor and the time rate of change of the momentum density, where I put, divergence of stress energy tensor is to be understood as it's a vector. It's a vector because we're taking the divergence of a tensor, and the divergence of a tensor could be a vector in this case. Really it's a vector of divergences, truth be told, if you want to, I don't know, however you want to talk about that. But that expresses, as I say there, the local conservation of field momentum in the absence of charge. And we talked about the dual roles of the Poynting vector and all that. Now, so here's the example that I talked about at the end of class. I just wanted to go through it because it's an awesome example and it deserves our attention. So you have a long resistanceless coaxial cable of length L, consists of inner conductor, radius A, outer conductor, radius B. It's connected to a battery at one end and a resistor at the other. The inner conductor carries a uniform charge per unit length lambda and the steady current I to the right, and vice versa for the outer conductor. You're supposed to find the electromagnetic momentum stored in the fields to start with. So this is actually a really, really pretty calculation. So here's the picture. We've got current flowing to the right in the inside, and understand the current's only flowing on this. There's a coaxial cable, right? It's essentially a pair of pipes. You can think of it as like a pair of pipes that are conductors. In practice, they're always actually a braided wire thing separated by like some sort of dielectric, right? Like that's reality. But if you're really rich, you could afford pipe coaxial, right? But anyway. So, all right. So the electric field is given by the usual, 1 over 2 pi epsilon naught lambda over s hat, because it's just from the positive charge in here. It's just outward, right? And that's as far as it goes because the electric field stops at the negative charge, right? So the electric field's 0 outside this thing. It's just in there. And we're ignoring any kind of fringing effects, let it be understood. Okay, this is a little bit of a toy model kind of example, but the magnetic field, then again, ignoring the finiteness and any kind of edge effects, we're assuming it's long enough that there's cylindrical symmetry so that we can write down the magnetic field as just this, mu naught over 2 pi I over s. And of course it wraps, as you know, the usual deal, cylindrically around like that. Now the Poynting vector then is 1 over mu naught E cross B, which we can straight calculate here as that. So it points very satisfyingly in the direction of the current flowing, right? So the coaxial cable is carrying energy from the battery to the resistor. Yeah, okay, great. How much? So, that's energy per unit area time. So if we integrate that power density over area, this right here, right? We integrate, and this integral is a little bit slippery, but just so you understand, dA is 2 pi SDS. So what we're doing is we're chopping the area up into little ribbons of thickness ds, and they're 2 pi s all the way around. If you want to, we could go back to a double integral and work out the details, but I think this is okay. And so the s, they be canceling, and that gives us a log of a difference, which is a log of a quotient. Excuse me, difference of logs, which is the log of the quotient rather. And this is IV. Now, why is that IV? That's not immediately obvious, I don't think. But V is the voltage difference, right? And if we work out down here, we can work out that the voltage difference, which, of course, if you look at the picture there, it should be VA minus VB. Like, look back up here. See VA? The voltage at A, right here. The voltage at B, right here. Also right here, which is also right here. So VA minus VB is V. Using usual theory of equipotentials, what wires mean. And as such, we have that the voltage at A minus the voltage at B, or the potential rather. And then of course, well, you can see that generically speaking, if we take the antiderivative, we get log of S, right, plus some constant. Who cares what that is? As if we take the difference in voltage, difference in potential, the C's, they be canceling, and we just get back to that, which is why we can go from this to IV. Again, the power is IV, but now we see that also through the lens of the Poynting vector carrying energy down the coaxial cable. I like this example. It's nice and clean, and not like the 4-page one I just got done telling you at the start of class, right? But there's more. To find the momentum in the field, we integrate that mu naught epsilon naught s over the volume. And since we only have fields from 0 to L and from A to B for S, then this is the integral we have to do. So we take that Poynting vector and integrate that thing. I was feeling guilty about my lack of bounds in the last page, so I added all 3 of them here, but they're all dumb because they just give you an L and a 2 pi. Well, not a 2 pi, but they give you an L and the phi just gives you the 2 pi, right? So you got mu naught lambda I, and then this gives us log, right? So anyway, this formula on its own isn't especially interesting, but there you go. Let's pause and understand what we're talking about here. We're talking about the electromagnetic field's momentum. That's what we've calculated here. This is the electromagnetic field momentum. Then next, Griffiths invites us to suppose the currents decreased by increasing the resistance. Apparently the resistor was actually a potentiometer. See? I took electrical engineering one point in my life. I know that word. Are you impressed? Okay, yeah, very good, yeah. So it's a variable resistor. We turn it all the way up. Apparently it goes to infinity, aka open circuit, right? But anyway, whatever. So as we do that, the current's decreased, and as that happens, the magnetic field changes, right? In lecture 22, we derived what happens if you have a current and you decrease the current. It induces a circumferential electric field. Do you guys remember? It was like at the very end of the lecture. And it was a cautionary tale, too. I talked a little bit about how the answer was unphysical. If you're too far away, it doesn't really make sense. But here we're not too far away, so it's a reasonable application of that example. Anyway, so that's the circumferential. This is not circumferential. What's wrong with me? I'm sorry. I'm thinking about the next example. My bad. But, whoa. I hope I didn't laser any of you. But anyway, so that's the changing electric field. The electric field, I guess it's also changing technically, but it's the electric field that's induced from the magnetic field changing, which is coming from the current changing, hypothetically. And then, of course, once you have an electric field, it puts a force on those charges, right? It puts a force on the plus charge and the minus charge. And so here's the plus, the force on the plus, the force on the minus. And what happens, of course, that this K is some complicated business that doesn't matter. And it cancels out here. And it just leaves you with that. But what is that? Well, we're not done yet. So that's the force that's applied as a result of, and I'm not giving you the details of how the current changes. It doesn't matter, actually. All right? Because if we want to calculate the impulse, right? This is, by the way, this is the mechanical force put on the insulators that are, excuse me, this is the mechanical force put on the wires that have the charge, the plus lambda and the minus lambda. It's a mechanical force, right? And so to calculate the mechanical impulse, the change in momentum, the change in the mechanical momentum, we integrate the force over time. And because you got this di dt, if you just integrate that over the time it takes for the current to go from I to 0, we just get that. But that is exactly the same. You see what's happened is we've changed the electromagnetic momentum. You make it a little bit smaller so you see both of them at the same time. We've changed the electromagnetic momentum when the current was flowing this amount to mechanical momentum. So momentum is conserved, it just changes form. It changes form in this example from electromagnetic at the start to mechanical at the end. And we have to have both in order to understand conservation of momentum. Which I think is that's a really, really cool example, yeah? This one, so finally, this is pretty much my last example for chapter 8. And I mean, he has another section on magnetic forces not doing work, but I'm not going to say much about that, except to say that I'm not going to say anything about it. So we have, just to recap, we've got energy density, we got momentum density, and newcomer here, angular momentum density, which is just R cross G. Of course, angular momentum depends on your choice of origin, right? But I think we're just going to put the origin somewhere on the axis. He never comes out and says that, but I think the equations that he writes betrays it. Because as we go on and study Griffith's example here, he more or less is putting R equal to like S hat, which is to presume that the origin lies somewhere on the axis, the z-axis. So here's the next example. You imagine a very long solenoid with radius r, n turns per unit length and current I, coaxial with the solenoid. There are two cylindrical non-conducting shells of length L, inside at A, which I've made red, and outside at B, which I've made green. So these are inside and outside of the solenoid. Of course, the solenoid, as the current wraps around, it establishes a magnetic field inside, which is in the z direction and uniform. Because we're assuming that it's a very long solenoid, so we have a nice boring constant magnetic field in the interior. All right, but we also have charge uniformly distributed on these cylindrical rings, all right, where that distance L is supposed to be small compared to the length of the solenoid. So he says, when the current in the solenoid at S equals to R is gradually reduced, then the cylinders begin to rotate. Now, if we go back, we talked about this another day. This is essentially just a concatenation of, we had a magnetic field going up through a disk. We had a ring of charge around it. And we talked about how if the magnetic field decreased, then the ring of charge would start spinning, right? But this is just that repeated. It's not one ring of charge, it's a whole stack of rings of charges, but it's the same idea. So we can see that if we decrease the magnetic field, then those rings are going to start spinning. But how? Well, that's what we look at next. So first of all, before we do that, figure out how they spin, we're going to figure out what's the angular momentum stored in the initial situation. Because we've got an electric field between the uniformly charged cylinders, and that is just the usual lambda over 2 pi epsilon naught s hat over s, but lambda here is q over L because we're distributing q uniformly over that cylinder of length L, right? So the charge per unit length is that. And that's only good for between A and B, all right? Because we got minus q on the outside on the outside shell, so the electric field would be 0 outside the outside shell. Approximately speaking. Of course, I'm neglecting edge effects and all that jazz, right? On the other hand, the solenoid, there's a magnetic field inside the solenoid for S less than R, the usual story, mu naught n I z hat. So we calculate the momentum density by taking mu naught epsilon naught E cross B, which works out to this, all right? And that's only good between A and R. So it's not, there's not electric field in the middle of the solenoid. There's only electric field in a certain like shell inside the solenoid, outside of the charged cylinder, but inside of the solenoid. I've shaded it there to illustrate where the momentum's non-zero. All right. And then we can calculate the angular momentum from that, which I have illustrated the direction of. Actually, no, that is the direction of the momentum, weirdly enough. Well, actually, it's not weird at all. That is the direction of the momentum. See, it's got a phi hat here, and it's apparently clockwise. How about the angular momentum? Angular momentum is given to us by the right-hand rule. So it's going to be like into the page. That angular momentum is actually in the minus z hat direction. So, all right, L is, and this is where he betrays the fact that he's taking the origin to be on the z-axis, right here. Because he's got R as SS hat, basically, when you look at the calculation, which gives us this. So there you go. We have constant angular momentum. This is angular momentum density. So to find the net angular momentum in this system, we just multiply it by the volume. Well, what's the volume of an annular cylinder? Well, it's just the volume, it's the height of the cylinder times the area of the annulus, which of course is pi r squared minus a squared. So this gives me the volume, right? And then there's the angular momentum density, so there's the total angular momentum. All right. So then the question is, what happens to it? Where does it go? Well, when the current's turned off, the changing magnetic field induces a circumferential electric field according to this handy-dandy formula right here. Notice that outside of R, it's like reciprocal with S, but inside, it's linear with S. So that's what happens as we change the magnetic field. We induce a circumferential electric field. The magnetic field here was vertical, right? So as that changes, you get effectively circumferential field lines. It's that old switcheroo he talked about earlier, where you can think of the like the current. If the current was in the z direction, we know magnetic field lines switch around, right? So if the displacement current is in the z direction, the induced electric fields wrap around. That's the thought process here. It's that quasi-static calculation that's being used. But anyway, those are the formulas, and then you can calculate the torque, which is the torque at B is R cross minus QE, because there's a minus charge Q at radius B, which gives you this. And there's also a charge, did I say, I forget which one's plus, oh yeah, there's a charge Q at A, which gives you that. So then we can calculate the total aw, come on, seriously? Oh yeah, it's fine, it's fine. Sorry, I was thinking I should have had, no, it's fine, I got lost. All right, so then we have the torque is here, and the torque is there. This is the torque on the outer and the torque on the inner cylinder, right? And if we integrate those, right, and so this, you gotta take this with a, like this right here doesn't make sense. I mean, I copied it right out of Griffiths, but this is nonsense. This right here, this is good. He doesn't write this, but this would make sense. Because like really what you're doing is you're integrating from like time 0 to time infinity with the assumption, or long enough time such that the current goes to 0. When you make the change to the current variable, then you're integrating from current I, the initial current, to current 0. That's what's meant by this rather sketchy formula, all right? But anyway, there's the net angular momentum developed by that torque And here's the net angular momentum developed by that torque, which are both due to the displacement current generating a circumferential electric field. And what is it? Well, what we see then, putting it all together, is that the electromagnetic angular momentum, which we worked out was this, the start of this example, it's equal to LA plus LB. Now these are literally mechanical angular momentum because we calculated the torque, we integrated the torque over time. That gives us the actual mechanical angular momentum of the rotating cylinders. And so you see that the electromagnetic angular momentum has been converted to mechanical angular momentum. To understand conservation of angular momentum in an electromagnetic setting, we must think about both the angular momentum in the fields and the angular momentum that is in the traditional mechanical sense. I really like this example. I know it's cheating. We're ignoring fringe effects. There's all kinds of, if you think too hard about it, I'm sure it falls apart. But the simplicity of, I mean, I know we've been talking about it for 10 minutes. How simple is it? But no, it's actually quite simple. This is a beautiful example. So anyway, that's chapter 8. You guys have any questions?
Is it possible to use this to launch things and violate law of momentum?
Is it possible to use this to launch things and violate? I mean, I think yes. Like if you take, okay, so like so I think in fact, if you take a hard look at like magic tricks, a lot of them are probably based on exactly this thing of like having momentum stored in like the electromagnetic sense and then converting it into mechanical momentum, because you can't see the electromagnetic momentum, right? So if you can hide a current and such inside your apparatus and then you don't touch it, but it just does stuff, right? Like it could be that. All right, where are we? So we are now we have reached chapter 9. Now chapter 9 is about a very interesting topic. So I'm going to start with so I'm going to I mean Griffiths is fine. He does what he does, but I'm going to jump ahead a bit. I'm going to jump to the middle of the chapter, kinda, and I'm going to get straight to the main derivation. And here it is. So let us talk about the wave equation. For electromagnetism. All right. So we begin with Maxwell's equations in empty space. All right. So what are those? The divergence of the electric field is rho over epsilon naught, but in empty space, there's no charge. So rho is 0. So we have the divergence of the electric field is equal to 0. We have the divergence of the magnetic field is equal to 0. We have the curl of the electric field is minus the time rate of change of the magnetic field. And finally, the curl of the magnetic field is equal to minus, or is it plus? I mean, I'll check on it. Yeah, plus. Mu naught, epsilon naught, partial E, partial T, right? So these are Maxwell's equations in empty space. Okay, so then, and I guess we could derive it if you guys want. Did you guys derive this one already? Like the curl of the curl? You've not done the curl of the curl?
Wait, no, we've done that.
You did that one?
Something like that, didn't we? I think we did.
We probably did.
Probably did.
I think, yeah,
I've seen
right?
it.
I mean, we okay. So,
Real confident.
well, we could do it, but since there seems to be there seems to be cautious agreement that this has already been done, so
Okay.
it's one of those ones that rests on the contracted Levi-Civita identity. You know,
This is familiar.
it's essentially a corollary to the when we sum over the two epsilon ijk's, we get a difference of deltas. And anyway, so this is nevertheless an identity of vector calculus, right? Which we could prove. And so let us take this for a spin. We have the curl of E is equal to the gradient of the divergence of E minus nabla squared E, right? Do the same for B, right? Do the same for the magnetic field. What happens there? I mean, same pattern, all right? So, curl of B of course, we can simplify. This is just equal to minus nabla squared E, right? And this is also equal to minus nabla squared B. Why? Because we know the divergence of the electric field and the divergence of the magnetic field in empty space is 0, right? But then we have the curl of, well, what is del cross E? What's the curl of E? It's minus partial B partial T is equal to minus nabla squared E, right? And I'll do it side by side here. The curl, let's see here, curl of B, well, that's mu naught epsilon naught, right? Partial E partial T equals to minus nabla squared B, right? Okay, but then we can pull the minus out, right? We've got minus, oh man. Whoa, such violence. Minus partial T of the curl of B, right, is equal to minus nabla squared E. And mu naught epsilon naught partial T. I'm commuting the time derivative in the curl of E over here. Equals to minus nabla squared B. All right. But then what? Well, the curl of B was what? So we've got minus partial T of mu naught epsilon naught partial E partial T. equals minus nabla squared E, and mu naught epsilon naught partial t of minus partial b partial t is equal to minus nabla squared v. Where, okay, like what are these equations I'm using? We should, give credit where credit's due. This is Faraday's law, right? And what's the other thing? Who does the credit go to for this? This is not, actually no, this is Maxwell's correction. But you got the right idea. But this is Maxwell's correction to Ampere's law, right? But I would just say that that's Maxwell's correction. So what does this give us? Cancel the minus, tidy things up here, and we have mu naught epsilon naught partial squared E partial t squared equals nabla squared E, and mu naught epsilon naught second partial derivative of the magnetic field with respect to time is equal to nabla squared B. Have you guys talked about wave equations in like your previous physics classes?
Online modern physics.
What's that?
In online modern physics.
You don't talk about the wave equation in online modern physics?
No, they did.
Oh, but it's online, so it didn't count. That is the spirit I want to see promulgate in the residential physics major here. I want there to be no respecter of those who take online physics. You guys should be like, you did what? Really? How dare you? That should be the feeling. Like, why weren't you in class suffering with us? Why do you take the easy way out? This must be the mantra. Negative social pressure is the only thing we have to keep people from taking the easy way out. So, right. I mean, what am I saying? This is the easy one, right? Like the online course is harder, right?
That can't be right. That can't be right.
No, guys, this is the easy one.
Isn't their test time? My time is effectively, my test is effectively untimed, right? That makes my course easier, right? Anyway.
Time isn't the issue.
Okay, so these are, all right, so I guess I need to, give me a second here. Okay, first of all, these are vector equations. So like, you have to understand that nabla squared, it means partial x squared plus partial y squared. In Cartesians, at least, this is what it looks like, okay? So it's the sum of the second partials. And so, like, for instance, this means that we have like mu naught epsilon naught partial squared Ez partial t squared is equal to partial squared, well, goodness gracious, nabla squared, Ez. But that means, golly, partial squared, partial x squared. What a mess. If the electric field is just equal to like 0, 0, and then Ez, then then we get, you know, mu naught epsilon naught partial squared Ez. That's not what I want to say. I'm sorry, guys. Give me a second here. That's not what I want to say at all. Dummy. In the context, if, you know, E has only Z dependence, just for the sake of making this a little bit simpler to think about, then you have mu naught epsilon naught partial squared E partial t squared equals to partial squared E partial Z squared, right? And so, like, I can erase, I mean, that it's the same equation, basically. Let's see here. Let me copy down a formula. So Griffiths actually derives the wave equation at the start of chapter 9 from like looking like waves on a string. I don't really want to do that in here, but I do want to quote the wave equation for you, which is this: partial squared f partial z squared equals to 1 over v squared partial squared f partial t squared. This is the wave equation for waves on a string with speed v. And so it's, you know, pictorially, he's got some pictures. Here's f, and here's z, and you might have, you know, some kind of repeating pattern, right? You've got some kind of, like, as he calls it, the wave train, and it just kind of, you know, with time, this is a snapshot in time, right? As time goes on, there's a wave that kind of propagates over in the z direction. All right? So as we look at, you know, nabla squared E equal to mu naught epsilon naught partial squared E partial t squared, and likewise for the magnetic field, we can compare. I mean, and I showed you in the context of we just have a z dependence, it just reduces to the wave equation, like, so like just z dependence. E equals to E of z, right? Then we could look at the z component, right? We'd have literally partial squared Ez partial z squared equals to 1 over, not 1 over, mu naught epsilon naught, right? Partial squared Ez partial t squared. Like that is, this right here is how that specializes in the most natural context to compare it to the wave equation on a string, right?
E could have other components besides the Z component.
That's right, right. This is just as a special context. Waves are much more general than this, but in that particular context, like E just having a dependence on, so in other words, it could, I'm not saying it's 0 in x and y, but it has to be constant in x and y.
It would be linear.
That would be a plane wave, yes. What?
Because that would just turn into partial squared e sub y, for instance, partial t squared equals 0, which is...
Well, I'm just saying that these two things are 0, right? So I'm just left with that. But like down here is better. But so I don't have much to say today on all this, but I just want to say one very basic thing, which is, and so I'm begging you to make a comparison with physics that you're not super familiar with, and I was much in the same place when I first saw this said. Like, oh, this is a wave equation. I'm like, what's a wave equation? Right? So, but if you go study what a wave equation is, this is like one of the fundamental ones. A wave equation, this is a transverse wave. The wave is transverse to the media. The wave is going this way, but the oscillation is that way, right? It's a transverse wave. This is the equation of a transverse wave. These are equations of transverse waves. And you can identify the speed from the coefficient. That's the interesting thing. See, because if you look at this, apparently the speed of the electromagnetic wave, right, 1 over v squared is apparently equal to mu naught epsilon naught. And so v is 1 over the square root of mu naught epsilon naught. But spoiler alert, that's the speed of light, right? So Maxwell's equations, with Maxwell's correction, imply that the speed of light only depends on what? The permittivity and the permeability of space. That's wild, right? Like, because the particulars, like when you study waves on a string, the speed of the wave, it depends on like the tension of the string, right? It depends on properties of the thing that the string is waving, like the string that's being waved, right? This is saying that electromagnetic fields, in the absence of charge, they can support oscillating solutions that propagate as transverse waves through space and time itself, where the speed just depends on mu naught and epsilon naught. And it can't tell, like so why is there electromagnetic waves in space? It's because some charge somewhere was oscillating up and down, as we'll study in later chapters, right? This has no accounting for if that charge that was oscillating up and down was going at some speed in one direction or another direction, like any kind of directionality of the source of the electromagnetic field. How on earth would that even be incorporated into this? This says already, if you really stop and think about it, that the speed of light must be the same in all frames of reference, which is wild. Because like the electromagnetic fields, the equations that they have to satisfy once they're out on their own, going through empty space, it doesn't matter how they started. Once they're in transit, they're stuck with these equations. And these equations say without a doubt that the velocity is that. So there's no accounting for like Galilean Doppler effects and things where if we throw a baseball on a train, it goes faster that way, and then if relative to the reference frame as opposed to if we threw it the other way, right? If you're usual thing, you have a train going 60 miles an hour, I throw a ball 60 miles an hour that way. Imagine I could throw a ball 60 miles an hour. Of course I can, but if I have a machine, but 120 miles an hour that way. But if I threw it 60 miles an hour that way, it would effectively be at rest from your perspective if you're not in the moving train, right? This is somehow saying that if you throw a baseball and the baseball's light, it goes speed c that way. If you shine your flashlight that way, it still goes speed c. It's not speed c plus 60 miles per hour or speed c minus 60 miles per hour. It's just this. In other words, Maxwell's equations themselves are already relativistic. They already are consistent with Einstein's special relativity. Once Maxwell made his correction, it was just a ticking, it was just a matter of time before people realized that Newtonian mechanics was mathematically inconsistent with these equations. However, if you sort through special relativity, Maxwell's equations transform naturally. So Maxwell's equations are already relativistic. It's a funny thing. But anyway, that's it for today. So next time we'll get into all the the formulas for how to deal with waves and the complex formalism, and I think we got to do like phasors basically. You guys should like that, right? Anyway, yeah.